You know, we all think of the standard CMOS inverter as the absolute workhorse of digital design. And it is. But honestly, it's not enough to build the kind of crazy powerful processors we have in our pockets and on our desks. To really push performance to the edge, engineers have this whole toolkit of specialized circuits. So today, we're going to open up that toolkit and see what's inside. Okay, let's get into it.
For decades, right, the whole game in the tech industry was Moore's Law. Just make the transistors smaller, cram more of them onto a chip, and boom, instant power upgrade. But that leads to this huge fundamental question that every single chip designer is grappling with today. Why can't we just keep doing that? Why can't we just shrink them forever? What is stopping us?
Well, the short answer is physics. It just gets in the way. When you shrink things down to the nanometer scale, the comfortable old rules of electricity just start to break down. You get all these weird quantum-level effects that you just don't want. But engineers, they're a clever bunch. They've come up with this amazing collection of tricks and totally different circuits to fight back. And today, we're diving into those very solutions.
So, first up, Moore's Law's big problems. As we push deeper and deeper into what we call deep submicron design, just making a transistor smaller, it's not a simple win anymore. It actually creates this cascade of new and frankly much bigger challenges. It's like you solve one problem, but you accidentally create three more.
And this really shows the three main hurdles we're up against. First, you've got velocity saturation. The electric fields inside these tiny little transistors are so intense that the electrons basically hit a speed limit. It's like a highway where it doesn't matter how hard you stomp on the gas, the car's just not going any faster. Then in the middle, there's sub-threshold conduction. This means your off switch, well, it's never really off. It's like a leaky faucet constantly dripping current and just wasting power. And finally, the transistors get so mind-bogglingly fast that the wires connecting them, the interconnects, become the bottleneck. You got these Ferraris for transistors, but they're all stuck in bumper-to-bumper city traffic. So yeah, we need some new tricks.
All right, let's get into our first tool. This one is all about one thing: saving space. When every last square micron of silicon is precious, you turn to something called pseudo-NMOS logic.
The idea here is actually pretty simple, but kind of radical. See, in normal CMOS, for every bunch of NMOS transistors you have pulling the output down to ground, you need a matching complex network of PMOS transistors to pull it back up to power. Pseudo-NMOS just says, you know what, let's not do that. It throws out that entire complex pull-up network and replaces it with just one single PMOS transistor that's basically always on.
And this right here shows you why that's such a big deal. Take a 10-input NOR gate. In standard CMOS, that's 10 PMOS transistors and 10 NMOS transistors, 20 total. But with pseudo-NMOS, you still need the 10 NMOS for the logic, but you only need that one single PMOS load. So you go from 20 transistors all the way down to 11. That's almost half. A massive, massive saving in precious silicon area.
But there's always a catch, right? There's no free lunch in engineering. The pro is amazing density. The con? Static power consumption. A big con. Because that PMOS transistor is always on, whenever your logic is active and pulling the output low, you've created a direct short circuit from your power supply to ground. It's constantly burning power. So you save a ton of space, but you definitely pay for it on your power budget.
Okay, on to our next tool, which takes a totally different tack. Instead of always aggressively pulling outputs high or low, what if we just use transistors as simple switches, just letting a signal pass along a wire? Well, that's the core idea behind pass transistor logic, and it is all about routing signals efficiently.
So how do you build this perfect switch? Well, step one is realizing there's a problem. A single NMOS transistor, it's great at passing a 0, a low signal, no problem, but it is terrible at passing a 1. The voltage drops, the signal gets weak, so the fix in step 2 is just beautiful. You put a PMOS transistor right there beside it in parallel. And guess what? A PMOS has the exact opposite problem. It's great at passing 1s, but bad at passing 0s. So the result, step 3, is when you put them together, you get a CMOS transmission gate. The NMOS handles the lows, the PMOS handles the highs, and together, they create a nearly perfect electronic switch. This is the bedrock for things like multiplexers, where you need to choose one signal out of many.
All right, now we get to the fun stuff, the speed demons. When your only goal is raw, blistering performance, making your logic switch as fast as is physically possible, you enter the world of dynamic logic. This is definitely a high-risk, high-reward kind of strategy.
Now, unlike all the other circuits we've looked at, dynamic logic isn't static. The output isn't always firmly tied to power or ground. Instead, the whole thing runs in two phases, all controlled by a clock signal.
And the key insight here is to use the tiny, natural capacitance of the circuit itself to just temporarily hold the output value as a stored charge. It's kind of like trying to balance a needle on its tip. It's really fast, but also really delicate.
So here's how that two-phase dance works. In phase 1, the pre-charge phase, the clock signal is low, and the circuit just blindly charges the output up to a 1. It basically assumes the answer is going to be 1 unless it's proven otherwise. Then phase 2, the evaluate phase. The clock goes high, now your logic block turns on. If the logic is true, it creates a path to ground, and whoosh, it discharges that stored charge, flipping the output to 0. If the logic is false, nothing happens and the output just stays high. This whole pre-charging trick is what makes it so incredibly fast.
And hey, while we're talking about speed, we have to give a shout out to another hero by CMOS. This is a cool hybrid technology. It uses standard, low-power CMOS for all the internal logic, but for that final output stage, the part that has to shout signals to other chips across long wires, it uses powerful bipolar transistors. These are totally different devices that are just fantastic at driving huge currents. They're the muscle you bring in for the heavy lifting jobs.
So, what this all comes down to is the digital designer's dilemma. And trust me, this is a challenge engineers deal with every single day. As you can see, there's no silver bullet, no one-size-fits-all solution. If you need to save area, you go with pseudo-NMOS, but you're going to pay for it in power. For signal routing efficiency, past transistor logic is awesome, but it adds a lot of design complexity. And if all you care about is maximum speed, you use dynamic logic, but you're giving up some robustness. It's all about trade-offs.
And that really brings us to the main point of all this. The true genius of designing a modern chip isn't about finding one perfect circuit. It's about being a master craftsperson with a full toolkit and intelligently picking and choosing, mixing and matching these different logic styles, putting a block of ultra-fast dynamic logic over here, a super dense block of pseudo-NMOS over there, all to solve one incredibly complex puzzle.
So, okay, we figured out how to compute things with amazing speed and efficiency using this whole advanced toolkit. But that really begs the next big question, doesn't it? We can process all this information, but where in the world do we actually store it?
Well, we are going to answer that in our very next explainer, where we will dive deep into the world of memory circuits, things like SRAM and DRAM. If you found this useful and you want to follow along on the journey, please do me a favor and hit that like button. It really helps us out. And of course, make sure you're subscribed so you don't miss what's coming next.